afternoon, everyone. My name is Latifa Youssef, and I will be moderating today's webinar, the first in the Rain Enhancement Hub series hosted by the National Center of Meteorology and organized by the UAE Research Program for Rain Enhancement Science. We will begin with an opening speech by UAE REP's Director, Mrs. Alian Mazrouri, who will be explaining the objectives of the webinar series.
Hello everyone. I'm delighted to welcome you all to our webinar series titled Rain Enhancement Hub. This series is hosted by the National Center of Meteorology and organized by the UAE Research Program for Rain Enhancement Science to highlight the various research and practical aspects of rain enhancement science and weather modification. This initiative aims to create a specialized platform for the members of the research community to share knowledge and expertise to achieve global water security. We are confident that these virtual sessions will reinforce UAE REP's mission of becoming the focal point for groundbreaking innovation in water sustainability through gathering prominent local and international scientists, researchers, experts, and stakeholders in this increasingly important scientific field. Ladies and gentlemen, at UAE Research Program for Rain Enhancement Science, we work with local experts and talented international collaborators to put an end to water scarcity by finding innovative solutions through collaborative efforts, by transferring knowledge and expertise in this field, and by enhancing and further developing the capacity in the field both locally and globally. Our webinar series will cover a diverse array of topics related to the global water security debate. They include targeted research areas of UAE REP's fourth cycle, introduction to weather, climate, and meteorology, role of artificial intelligence in weather forecasting, and rainfall trends in the UAE and the Arabian Peninsula, among others. Distinguished guests, in closing, on behalf of the National Center of Meteorology and the UAE Research Program for Enhancement Science, I would like to thank all of you for attending the webinar sessions. I wish you all a fruitful participation in the event that will enhance our collective efforts to achieve water security.
Thank you, Mrs. Alian Mazrouri, for your remarks. Before we begin, I would like to inform you all that there will be a Q&A session at the end of the webinar, where you can type your questions in the comments section, mentioning the name of the speaker you wish to direct your question to. We will do our best to address as many questions as possible with the time available. Allow me to introduce our speakers and the topics they will be presenting. First, we have Dr. Diane Terblanche, Weather and Climate Consultant at the World Bank and former Director of Research at the World Meteorological Organization, who will be giving a presentation on the history of hygroscopic flare seeding for rain enhancement. After that, Mr. Sufyan Farah, meteorologist and cloud seeding expert at the National Center of Meteorology, will present the history of cloud seeding in the UAE. We will conclude the sessions with our final speaker, Ms. Noor Al-Shamsi, weather forecaster at NCM, who will present the research and development efforts of NCM in the rain enhancement domain. I now welcome Dr. Diane Terblanche to give his presentation.
Good afternoon, everybody. I hope you can hear me. So I would like to discuss with you this afternoon a brief history of hygroscopic flare seeding for rain enhancement. There's always been really an issue about water. Through history of mankind, we tend to be having either too much or too little of it, and the wish to be able to have some control over that has been part of human history almost right from the beginning. But as our numbers have increased around the world, water is clearly now a very scarce resource. It's the source of life, and therefore we need to look very carefully how we manage our water resources and its implications to food security, health, and also all the other sustainable development goals that we are trying to address. And it's especially in the arid and semi-arid parts of the world where water has become a central issue. So in this light, I would like also to share with you some of the history about weather modification and rainfall enhancement specifically, highlight a few things regarding the various approaches, and give you an idea of where we are after more than 50 or probably 70 years of research in the modern era of rainfall enhancement. And then I would like to share with you something about the hygroscopic flare, and I will tell you more about that, how it was developed and tested, and some of the results we've obtained. And it's also this technology that's currently being used in the UAE and many other places around the world, although there's still more to learn and more to understand. And then I will conclude with some of the current and future work. So let's look at water as a scarce resource. Water scarcity is a global, significant, and accelerating problem, as I mentioned before, for about 2 billion people worldwide. So it's a significant, a third of the world population almost, that faces issues related to water scarcity. And as I mentioned, this is hindering growth in food production and harming human health, but also, most importantly, it's holding back economic development. So water is such a basic requirement for life on Earth that humans, since the earliest times, have had the desire to influence it, especially in terms of its timing, when it's raining, or the amount of rainfall. And in that little map there, you can see those parts of the world where you have the number of months in which water scarcity is more than 100%. So if it's the darkest red, it's 12 months of the year, and if it's green, then it's 0 months of the year. So then you see that across the north of Africa, the Middle East, into India, even places in China, big parts of the USA, Southern Africa, Australia, parts of Argentina are the places where we have the most serious issues. It's also interesting that these are the regions of the world where you have advanced economies relative to the continent in which they are. And so this is a serious thing for global development and human progress. So let's look at the earlier studies and approaches. So in the old days, people used to dance around a fire in an attempt to influence the weather. But the modern age of weather modification actually started just after the Second World War. And I will focus on two basic approaches. The warm versus the cold rain processes. In other words, the warm process is where liquid water is involved, and the cold process is where ice crystals are involved. And as I said, we've had many years of research and development. So this is 1946, and this is some of the first attempts by Schaefer, Langmuir, and Vonnegut in the USA at General Electric, where they created some artificial ice crystals in a cool box. They then actually went out into the field and seeded some thin layer of cloud with dry ice. Dry ice is a very cold substance, and if you throw that into a cloud where there's super cold water, it will just glaciate that very quickly. And that is a very convincing evidence that man is actually able to modify the weather, because you could see exactly where the aircraft flew in that continuous deck of clouds, and actually some light snow fell from the area where it was seeded. So an early triumph in weather modification, but we will see that the route is not always that easy and the cause and effect that simple. These are very simple clouds. It's nothing like we have most of the time over the UAE and other arid and semi-arid places of the world. So this is just a diagram that gives you an idea, without going into much detail, about the warm versus the cold rain processes. On the right-hand side, you have the warm rain process, and you can see it's more a simple process. It's more linear. You have aerosols in the atmosphere. That's actually the dust particles. Some of them have special properties. They act as cloud condensation nuclei because each drop needs to form on a nuclei. They then grow into droplets, and they grow through condensation and coalescence. That's the process where they collide with one another into drops, then eventually they fall out as rain. So that is the most simple way of looking at the warm rain process. On the cold process, you will see that some of these aerosols also have the unique property that they can act as ice nuclei, or the IN indicated there. So then they create ice crystals in clouds. And then you can see the process becomes much more complicated. It turns into snow, or it can go into graupel, and then it starts interacting with the left-hand side where there's still some liquid water. And you can see at the bottom you've got different things coming out. It can either be hail, or it can be raindrops, or it can be snow. So the ice process, or the cold process, is a complicated one. And I think this figure also tries to tell you that there's often interaction between the two. So it is most probable that if you make changes to the warm process on the left-hand side, that it could also impact on certain characteristics of the cold process in that same cloud higher up. So you can see it all starts with aerosol particles, minute particles, 1 micron or something like that in size, and eventually it turns out into precipitation. And just to give you an idea, a condensation nuclei is, say, 0.2 micron. The average cloud droplet is about 20 micron, 20 thousandths of a millimeter. A large cloud droplet, like you will find in fog, is about 100 micron. If you have very light drizzle, it's like 300 micron. And an average raindrop is about 2 millimeters in diameter, and they don't really go bigger than 6 millimeters, because then they become hydrodynamically unstable as they fall through the atmosphere. So on the right-hand side, you can see if you have a larger droplet falling through a population of small droplets, it will fall faster. And then there's a chance that it will collide and coalesce with some of the smaller drops, and in that way it will grow bigger and bigger. So this is a very important process in rainfall formation. So as I mentioned, if you look at weather modification, there's the Journal of Weather Modification, a publication, and the anniversary edition a few years ago indicated on its cover some of all the things that happened through the year. It's just like a snapshot. But on the right-hand side, you can see countries where weather modification is taking place around the world. The blue, which coincides very well with that figure that I showed you right in the beginning regarding water scarcity, is about rainfall enhancement. The red is about hail suppression, and the green is where there's a combination of both. So you can see it's at that stage, is a few years ago, about 56 countries around the world had active projects or experiments going on. So now let's look at this hygroscopic seeding thing. Now I'll give you a South African perspective because all that work was done here. So what I mention here is from what we learned here in South Africa. Only 10% of the moisture transported across South Africa falls out as rain. So in the atmosphere, there's a lot of moisture that's been transported across the country, and only about 1/10 actually falls out as rain. The other 90% comes in the one side and leaves the subcontinent on the other side, from the Atlantic to the Indian Ocean. We also know that over especially the summer rainfall areas of South Africa, a large percentage of the annual rainfall is produced by convective storms. Convective storms are our typical thunderstorms that produce heavy downpours with lightning and thunder. Now, these storms are also not very efficient in converting all the moisture that it processes into rainfall, because many of you will also have seen that if you have a thunderstorm, they often have these large anvil clouds. And after the thunderstorm has died out, you have this very high level of cirrus cloud left, where a lot of the unprocessed water that didn't come back to the ground is actually left in the atmosphere and slowly evaporates. So on average, these storms only processes about 30% of the moisture that goes into them. So we see some inefficiencies here. Only 10% of the moisture falls out, and in the storms that produce the bulk of the rainfall, only 30% of the moisture that is being processed falls out as rainfall. Now, as I mentioned before, in the updrafts of the moist air at the bases of these storms, each drop condenses on an aerosol particle known as a cloud condensation nucleus. So you can imagine now that these nuclei, their population, their concentration, their sizes, their chemical and physical properties, has actually got a very large impact on the characteristics of the cloud that will form, as I will show to you later. So this is a typical cumulonimbus cloud where you have updrafts where moisture is brought in from the boundary layer, where condensation falls place, the big anvil cloud at the top, and rainfall falling out in the cold downdraft. And there could sometimes be hail and microbursts, which is an issue for aviation, even tornadoes, and so on. So what we did in South Africa, we have a wide variety of climatic zones in South Africa. So we have coastal areas and we've got semi-arid interior regions. And we were fortunate that we had well-equipped and instrumented microphysical aircraft so that you could fly through a cloud and do measurements of the drop size distributions and many other things. Now, this graph simply shows you in green what the numbers and the sizes of the droplets just above cloud base looks like in a cloud over the semi-arid areas. And you can see that you've got a peak around about 10 micron in size, a fairly sharp peak. And the blue line shows you if you then move to a more coastal area, more maritime area, that you have much less droplets, and that the maximum size is about 25, the maximum concentration of big drops around 25. Now, these clouds more or less have the same liquid water content, but how the liquid water content was spread amongst the droplets were completely different. So in the semi-arid cloud, we had like 400 droplets per cubic centimeter, while in the maritime cloud, it was only like 61. And then you have this very narrow distribution where many of the drops are of the same size, while in the maritime cloud, you had this much broader distribution of sizes. Now imagine, as I said before, if you have large drops and small drops interacting, the large drops will fall faster than the small drops, and there's a chance that they will collide and coalesce into bigger drops. So immediately from this, you can see that a maritime cloud is more efficient in producing rainfall than a convective cloud over a semi-arid region. And this is the basis of what then followed. And we know this, that over desert, semi-arid areas, you really need clouds to develop to very high vertical depths before they produce rainfall, while in maritime areas, even small, what appears to be insignificant clouds can sometimes produce quite a lot of rain. So we then developed this hygroscopic flare, and this is just the size distribution of the particles after burning. So what we really attempted to do is to modify those condensation nuclei on which the droplets form in the continental semi-arid type of clouds to act more like ones that are in a maritime environment. This is just one of the bigger particles. It's just a salt particle of sodium chloride, potassium chloride mostly, and some magnesium oxide from the burning agent. And this is the aircraft that we operated in South Africa. We had 5 research aircraft, including a Learjet, and so we were actually well equipped to do good work. What was also interesting is that we were completely isolated from the other facilities of the Weather Service or the Water Research Commission. We had our own facility where we could just concentrate on this, far away from bureaucracy and all the other things that sometimes takes up one's attention. So it was a great time in my life as well. We had a network of weather radars across the country, and we were the first ones to use the so-called Titan software to do storm tracking. Actually, Titan itself has also got its roots in South Africa, because the author or the creator of this system is a South African, and he did the first work on this before he went to NCAR in the USA. And this is just some figures. On the left-hand side is something that was done recently also in the UAE, where you fly one aircraft behind the other, and you measure what comes out of the flares when you burn them in terms of their sizes and concentrations. And on the right-hand side is an aircraft busy seeding, and that white that you see there is not actually smoke, but it is droplets forming on these salt particles being released by the hygroscopic flares, and you can actually see how it's been drawn into the base of the cloud a short distance behind the aircraft. So as I said, we had well-instrumented aircraft, so we could fly through clouds and do detailed measurements of the updraft velocities, the temperatures, the wind, have images of the cloud particles. And I must mention that this is like 25, 30 years ago. So this was really advanced at that stage to be able to do this and use these tools so well. And we also did modeling work to compare if you take a typical continental air mass and you introduce these particles like we got from the flares into it, what you will see. And on the left-hand side is the natural cloud and the evolution of the drop size. This is a fairly simple microphysical model. On the right-hand side, you can see a big change towards the larger sizes as time goes on, which is an indication that there's some hope from a theoretical point of view. So what I've shown you now is some physical studies where you do measurements, some modeling studies where you use the theory to try and explain what you see. And then the third one was the statistical studies, similar to what you do in the medical profession or in the pharmaceutical industry when you, for example, test COVID treatment, where you do a placebo treatment and a real treatment in such a way that you have unbiased population, and you can then analyze it. So we did the same with the clouds. We selected clouds. We had a set of envelopes kept at the radar that if you open it, it said either seed or no seed. It was numbered from 1 to whatever. And in the aircraft, you had a similar set of corresponding envelopes. So the radar operator would, after a suitable storm was selected, would open his envelope. That would say seed or don't seed. And then the aircraft scientist or pilot will open his envelope with the same number, and that will say yes or no. So the combination of seed and yes implied that the cloud will be seeded. The combination of seed and no implies the cloud would not be seeded, and so on. In any case, at the end of the day, the radar operator didn't know whether this cloud was actually seeded or not. And the aircraft pilot or scientist couldn't just pick the best clouds to be seeded because they didn't know whether it's going to be seeded or not, even if they opened their envelope, because they were dependent on what came from the radar operator. So in this way, you eventually have two groups that you can do a statistical analysis of. And this is the results of that, published in the Journal of Applied Meteorology, as I said, 24 years ago. And in blue, you can see the seeded storms. This is a quartile analysis. In other words, the top blue and red graph indicates seeded storms versus non-seeded storms. And you can see that the seeded storms produced more rain for longer. In the middle two lines, you can see red and blue again for the medium-sized storms, and then right at the bottom, the small storms. So quite a clear statistical significance that came out of a sample that was about 120 storms that took part in this so-called randomized experiment. So then our colleagues at NCAR decided to repeat the same experiment actually in Mexico. They used the South African flares, they used the South African pilots, and repeated this experiment in Mexico, and that is the similar results. I will not go into that. But this was actually quite encouraging to be able to do the same thing in two different parts of the world and basically getting the same results. Now, we continued the work in South Africa for a number of years after this, and developed methods that you could try and evaluate operational seeding. And we did some calculations on the cost of additional water and all that. It's all published, so it's available. This is just the target area of the operational work. And just to give you an idea of what you should think about is, we worked out that the seeded storms produce about 16 million tons of rainfall each, compared to 8 million tons of the control storms from that experiment. So if you take an area and you want to increase the rainfall by a certain percentage, you need to work out how many storms you need to see to be able to do that. I mean, this is all just logic. So we worked out that therefore, if you want to increase the seasonal rainfall by about 10%, and the area rainfall annually there is about 600 millimeters, you need to seed 75 storms to hopefully get to the 10%. Otherwise, the calculations just doesn't make any sense. We also, as the radar ran 24 hours a day, like most do these days, we could do a storm climatology where you could see in different months of the year the number of storms that you see, looking at the time of the day when you see most. And this is the one that told us that there's enough storms. You have 290 legitimate seeding candidates in the region per year. So it won't be that difficult to seed the 75 that you need to get to the 10% increase in rainfall. But this graph also tells something else. It tells you that during a certain hour or two of the day, there's a huge number of storms that actually develop. So logistically, it becomes a problem whether you will have enough aircraft to be at the right place at the right time for all these storms. And this is when we started talking to the military to look at the things that we are looking again now, the use of unmanned aerial vehicles to deliver the seeding material. And it didn't get very far because at that stage, the legislation for civil aviation was still far, far away for UAVs. And but we went through all the steps and we're quite excited about this. Something else that was done that's, I believe, always important is to look at the environmental considerations. And you will not be able to see the detail here. But there are lots of things that you need to take into account when you assume that you can increase the rainfall over an area. Issues related to hail, soil physics, soil fertility, reduction in fire risk, some of them good, some of them bad. But, and of course, then issues like possible toxicity of seeding materials. So these things are all really very important. So in conclusion, this whole experiment concluded with the fact that if we could seed 75 storms over 100 by 100 kilometer target area in South Africa, we could increase the rainfall by 10%. We know that there's enough storms to do that. The climatology tells us that. And we believe that this technology holds a lot of promise for water augmentation around the world. And this is why it's also still being used very widely. Although I'll be the first person to say that there are still many questions that we need to address and things that we don't understand well. So eventually this whole South African experience was also the recipient of a UAE International Prize for Weather Modification in 2006. And there's a little bit of a story about that. So the future and current work. So the UAE REP is really now the leading global research program in rain enhancement science in the world. And the UAE really took the lead to energize this field again. And we've seen a lot of excitement into this field, which is really important for the future of humanity in terms of water resources. It has fundamentally supported advances in the field of rainfall enhancement. It's again fostered this global research effort and scientific cooperation through all the sponsored and supported research projects. And this is really important because this is a difficult, complicated field to deal with. I can tell you, I believe that the field of rainfall enhancement is much more difficult than to transplant the human heart. It is complicated, and so we need to have a global community that can work on this. The UAE also supported the World Meteorological Organization to conduct a review of the status of rainfall enhancement, and there's a peer-reviewed report available and an article that was also published in the Bulletin of the American Met Society. A lot of capacity development and technology development has taken place and is taking place still. Significant contribution to the published scientific work and to numerical modeling, and also these regular forum on rainfall enhancement that we have had in the past, and even in events like that of today. So just to give you an idea, the outreach of this program is just amazing. There's like 70 countries that's involved, and all the stakeholders, and 500,000 researchers involved. I mean, this is really, really significant. And then you can see also in those first 3 cycles, the growth in the interest and the number of submissions and the number of scientists involved just going up and up. So here's just a slide giving you a summary of all the different 9 projects that's been awarded up to now, and basically the fields in which they are, ranging over a number of topics, from numerical weather prediction to creating artificial updrafts to assist in triggering clouds to changing the surface properties over UAE from a theoretical point of view to ice nuclei and many other things. So this is really an exciting venture that these scientists are on, thanks to the efforts of UAE REP, and I will conclude there. Thank you very much.
Thank you very much, Dr. Dion Terbanj, for your talk. Allow me now to invite our second speaker for the webinar, Mr. Sufyan Farrah, to give his presentation.
Yes, good evening. Thank you, Dr. Latifa, for introducing me. I would like to thank all the gentlemen that they are joining us for the Rainfall Enhancement Hub here. Actually, I would like to mention at the beginning that to address you before the historical experiments and approaches to the cloud seeding in the UAE. I would like to say that the country is not suffering from the scarcity of fresh water, since we have plenty of desalination plants, but we are crucially suffering from the shortage of natural water resources such as rain. So at the beginning of cloud seeding has been started in 1982. It was the first attempt to the cloud seeding. It was under the umbrella of the Abu Dhabi municipality. It was focused all over the western region for only 50 days to test the glaciogenic cloud seeding effect. Actually, the government took the commitment through the National Center of the National Center of Meteorology here in the UAE, and we contacted the National Center of Atmospheric Research from Colorado and Witwatersrand University from South Africa. In addition, the other procedures or aspects has been taken through the Space Agency from NASA and NOAA, and WMO was involved in the UAE prize for the cloud seeding researches. At the beginning, we started with to work as one group, all that being mentioned. We used different probes to measure the aerosols and background aerosols of the atmosphere here, and also to measure the particle type and sizes and distributions. So we used many probes like PCASP, FSSP, 2DS, 2DB, and so on. And this was actually started at the beginning of 2001. And despite that, the country has made many experiments, but before, but it wasn't following the scientific basis. But from 2000 and 2001, we started to manage the cloud seeding with a scientific basis. We had installed more than 95 automatic weather stations over scattered parts of the UAE. Imagine that the UAE is a little small area, but it has diversity of different topography. We have a coastal, desert area, and mountainous regions. All of these areas been covered by monitoring for the weather elements such as temperature, pressure, wind direction, speed, humidity, solar radiation, and so on. And in addition, we installed about 30 rain gauges. These weighing scale rain gauges was to fill the gaps between the stations, as well as the clouds available here especially during summertime, are in small radius, about 6 to 7 kilometers only. Also, we had different density of network, 5 stationary radar networks being installed over Dubai, Abu Dhabi, Mazera, and Al Ain area, and Khsera to the southwestern region. And this network, national radar network, has covered most parts of the UAE with a full coverage. Of course, these radars has a Titan aspect, so it has can define different features of the cloud, vertical integrated liquid, and the volume, the precipitation flux, and so on, which is essential for the cloud seeding operations. Of course, we did study the different resources of aerosols, as well as the aerosols are the main factor to inhibit or to activate the cloud formation and development. So we did many studies with the cooperation of Space Agency, NASA, from USA. And we found, for example, that during winter time, if you have a vigorous low pressure affecting Iraq and Kuwait, where the northwesterly flow exceeding 15 knots can erupt the dust and moving toward the country and evolves the atmosphere, make reduction of the visibility, and some of these pollutants carried by this dust storm or dust pollutants can affect the glaciogenic process in the cloud development. In addition, that the Interquarter Desert in the south of UAE has good particles that enhance the formation of the cloud and the accumulation. But unfortunately, these particles are giant in size, in spite that it is coated by sulfate, which has a good affinity for the moisture. The other resources are coming from the Indian subcontinents. These materials are organic. Most of these are organic because they are using the feast, the down from animals, and can be trapped and travel many thousand kilometers toward the country and confluence there. These organic materials also has a different effect on the cloud formation. And from the Sistine Basin to the eastern part of Iran, can only 10 knots erupt the dust and be carried by the easterly and sometimes from the southeasterly when it is moved a little far from to the east of Iran, and can these particles mainly has a very, very fine particles and whitish color, and can affect the heat budget of the atmosphere here. And of course, the sedimentation of these particles are very difficult and also can affect the formation of the clouds. So all of this has to be studied and to see the influence of these particles on the cloud formation and development. So we started to do the cloud seeding with different experiments. For example, this can illustrate the airplane being launched from Abu Dhabi airport to the eastern region. And of course, through this image, you can decide which cloud has to be seeded or not. Of course, another way to study the different phenomena in the UAE to see is it feasible to do the cloud seeding or not. During the winter season, for example, we have about 4 pressure systems are affecting the country. It starts from the western islands, covering the sea and the islands, and moving toward the north. At the first attempt, or the starts to come close to the coastal areas, it developed to be heat and cumuliform clouds and amenable and suitable for cloud seeding. But within the coming, after 2 days or 3 days, these clouds will start to be like stratiform clouds that is not suitable for cloud seeding, in spite that continue giving some results. During summertime, this is Viz 5 can show the animation of how once the air masses coming from Oman Sea, humid air, objected by the mountains, and the cloud starts to develop. Developing there, of course, for cloud seeding operation, we have to seize the first stage, cumulus stage, to be at the base of the cloud and to see. This another one can show the demonstration of how the clouds are developing there. Of course, this mountainous terrain is a mercy from God to the UAE. It is separating the UAE with Sultanate Oman to the eastern part. The other can show the wind paths, how they are confluence at the both sides, coming from Arabian Gulf and from Oman Sea. This confluence, with the additional support from the mountains, can develop the cloud into convective or cumulus conjustus, and so on. Talking about the most convective clouds are frequent during summer season over the northeastern region or the eastern terrains that extends from the northwest toward the south, and the other location can be seen over the western region due to the fluctuation of ITCZ. And this is actually some different from one year to another. Sometimes, for example, 2017, we had a good heavy rain over the western region in July. So to summarize our historical experiments in the UAE from 1982 to 1992 during winter operation cloud seeding program that, for example, been started to the western region, and 2001 during winter and summertime we had the visibility study to study the atmospheric and microphysical processes and crystallization of the clouds. 2002 and 2003 we continue on studying the visibility of cloud seeding operations. And in 2003 and 2004, we joined the randomization cloud seeding project, that statistical randomization method to see how the effectiveness of the cloud seeding on the cloud. It was showing that we collected about 150 weather cases on different days, and we found out the rainfall enhancement was in a ratio of 10 to 15%, an extra amount of rainfall while in turbid atmosphere, while this ratio elevated to reach about 25% in clean atmosphere. But mostly the atmosphere of the UAE, especially during the summertime, are under the influence of concentration of pollutants and aerosols. So in 2005, yes, we find that it is amenable to do the cloud seeding operations in the UAE. And we started the operational seeding over the eastern mountains in summer 2005. 2006 and up to now, we have implementation of cloud seeding over different and scattered parts of the UAE throughout all the seasons of the year. There are many different countries that they are using the cloud seeding for the purpose for hail suppression or precipitation enhancement or both. As Dr. Dion mentioned, that more than 56 countries are working on cloud seeding. Thank you for joining us to Enhancement Hub. Thank you. So I will be ready for any question you like.
Thank you, Mr. Sufyan Farah, for your presentation. I now welcome our final speaker for today's webinar, Ms. Noura Shamsi, to give her presentation.
Hello, everyone. My name is Noor Al-Shamsi. I would like to thank Dr. Latifa. I'm from the Numerical Weather Prediction and Research Department at NCM, and I would like to present the progress report. We've been studying the operational cloud seeding over the country, as it is very vital to know what are we doing right and what are we doing wrong. So here is a few examples of, or a progress report of what we've been doing. So first of all, I would just like to say any suggestions or any recommendations are more than welcome. We want to hear from your side. We'll start with radar parameters. We have data from 2002 till a few days ago or recently. It's updated regularly at NCM. We have climate of storm clouds from the radar, and we have trends of rainfall from GPCC data. So the global precipitation data, reanalysis data. Just to make one thing very clear, we are using dynamic seeding instead of static seeding in the country. Static seeding is where flares are burnt or flares are deposited at the top of the cloud, where dynamic seeding is where we burn flares at the updrafts of the cloud, and that is the most suitable method for the country and for the clouds that develop in the country. First of all, timing is very important. It was the most important agent or the most important parameter that we have. We've studied more than 100 cases or more than 100 convective storms, and we found that the relationship between maximum reflectivity and the cloud lifetime is inversely proportional. So we would recommend cloud seeding as soon as the cloud starts to appear on the radar. So if you seed the convective cloud at 15 dBz, you're expected to have a higher cloud lifespan than if you seed it as a very high reflectivity. And here in the figure, it actually shows a case where a cloud was seeded twice before it appeared on the radar and then shortly after. So in total, 6 flares were burnt, and through the radar parameters, volume, aerial coverage, it showed remarkable results. Then moving on to location, updrafts and are very important, as we all know, but updrafts and seeding at the path of the cloud movement actually have the most effect on our clouds. So in this case, as we can see from the figures, the gray column shows the time of seeding. So shortly after the cloud appeared, it was seeded at 12 UTC. And after that, we can see the increase in volume, precipitation flux, aerial coverage, even dBz and echo top. This can be easily maneuvered, or we can easily maneuver our pilots through our forecast, and especially at 700, 600, and 500 hectopascals. Our radars also have forecasting techniques that make it easier for us. Number of flares burnt. So in this case, it was quite amazing, and on the 9th of August 2019, a total of 16 flares were burnt in a convective cloud, making it deep and extremely useful to the country's groundwater reserve. So we can see from the reflectivity the amount of rainfall that fell from the reflectivity shown here. We can tell that the amount of flares burnt were appropriate. This is not always suitable for every single cloud, but when you start seeding early on, and then you you manage the development of the cloud, you can it can result in something quite amazing, such as this case. So intense hygroscopic seeding go a long way. In some cases, but not all of them. Merging is personally what I love the most. We are basically creating more clouds from two adjacent clouds. So between the echoes, I'm going to call them echoes because we're dealing with radar here. So between the echoes where downdrafts interact, we increase the convergence and it results in the formation of new towers. Those towers ultimately result in the merger of a cloud. So the aerial coverage increase, cloud top height increase. As we can see from this figure at the right, the seeding time was at 12:03 UTC. But the cloud top seems to be constant, and that is because it exceeds the beam of the radar, which means that it did incredibly well. The merger resulted in intense amount of rainfall, of course, more intense than if it was done in any other spot or at the path of the cloud. So sometimes we do have to prioritize the location of seeding. Next, there are a few cases, 4 cases, 2 of them which were seeded and 2 that weren't seeded. Before even going into the figures or reading anything, it is apparent which clouds were seeded and which weren't. By the lifespan, by the echo volume, seeded clouds have more of a chance to redevelop after seeding. And that's what we saw in a lot of cases. I do really wish that I can show you all of the cases, but it would take hours. But this is the biggest proof that we have. Unfortunately, this is more operational and less controlled. So all of those cases happened on the same day, around the same location. The first one, or we can see the black line, is that the cloud started to appear at around 8 or 9 UTC. And due to seeding, it lasted for longer than 90 minutes. Another cloud, which wasn't seeded, let's see the green line, lasted for around 48 minutes. And the timeline here is very important. The volume is very important, as we all know. Each parameter, each minute gives us a chance for more precipitation. As a country that really does need more water reserve. So here we did a study between seeded and unseeded storms. Of course, this is not, this needs more studies, and we are doing more studies. But we wanted to know roughly the amount or how much of an enhancement is happening. The figure to the left, we compared the 76 seeded clouds to 172 unseeded clouds or storms. And the figure to the right, 65 to 87. So we have rough numbers. They are not exact, and we're still looking to get more exact numbers or more methods to get a number, just a number that we can really answer the questions that, of course, everyone asks us as meteorologists or atmospheric researchers. How is cloud seeding affecting the country, or how is it affecting the cloud itself? So here, for example, we can look at duration. We saw a 47% ratio of enhancement from 47 to 65. Aerial coverage from 34 to 72. Volume from 61 to 159. This is extremely important because it really does affect the amount of precipitation that is falling. Top height, maximum reflectivity, and mass, everything is showing us a ratio of enhancement. And this was our main priority, is to, first of all, have something to prove that the operational cloud seeding in the country is increasing. Other than just looking at precipitation itself, sometimes we are studying the cloud. And I think it is very essential. Next, we went to climatological evidence. So we do have studies on individual stations. We have studies over areas in the country. We wanted to supplement that with, or have something to supplement our results, GPCC data. Something that I loved in this work is having a comparison between our pre-seeding period and post-seeding period. So here we have 1989 to 2002, which is pre-seeding, 2002 to 2016. We can clearly see a decrease in all of the areas and an increase post-seeding in almost all of them. The ratio of increase might change from an area to another, but we still have an increase, which is good to us. Area 3, which is the internal area of the country, had the most, along with station data, we can see it was the most shocking result. Area 2, which is closer to the mountainous area, also showed an increase. But when looking at the topography of the country, myself, I am more interested in, well, I'm interested in the entire country, but the mountainous area, we almost have convective clouds in summertime more frequently. And we're dealing with that very well. The internal areas are mostly desert areas, which I believe through our study and through numerous data sets and methods is showing really good results. And that's what I would like to highlight. The operational cloud seeding in the country is not just affecting, or is not just improving the mountainous area, but also internal desert areas. I hope this presentation or this update on what we're doing has helped inform you. I would also like to know any suggestions or any methods that any scientists would like to share with us. Thank you.
Thank you very much, Ms. Noor. So we've received a few questions from the audience, and I would like to now welcome our three speakers back to the stage so that we can address them. Welcome back, everyone. Okay, I can address the first question to Dr. Dion. So one question we got was, how is rain enhancement being developed on a global level, and what can we expect to see in the future?
Latifa, just say that again.
Sure. How is rain enhancement being developed on a global level, and what can we expect to see in the future?
Okay, thank you very much. As I mentioned in my talk as well, the UAE REP plays a central role in the development of this technology. It brings together scientists from around the world. And we now, fortunately, have new technologies, from instrumentation to seeding material, also to new analysis techniques that involve artificial intelligence, using data from new generation of satellites, big data, improvements in modeling. So, although we have known the theory of cloud development and microphysics for many decades, we only now have the tools to move ahead. And I believe that this specific program actually is the great facilitator to make all of this happen. So I'm very optimistic to see that we will see some breakthroughs in the future, especially concerning those outstanding issues of how do you actually show cause and effect in a physically understandable way, and being able to actually evaluate the results of a seeding experiment in terms of rainfall on the ground, because it's all about water at the end of the day.
Thank you very much, Dr. Dion, for your answer. We can direct the next question to Mr. Sufyan Farah. One audience question is, how do we measure the effectiveness of cloud seeding in the UAE?
Yeah, as mentioned in before, that we had the statistical randomization method, and we collected about 150 weather cases at that time in 2003, summers 2003 and 2004. And it was showing that same like has been explained by Dr. Dion, that using different envelopes, including yes or no and so on. So it revealed that an extra expelling out of water from the cloud is about 10 to 15%. So this is actually in the turbid atmosphere. But in clean atmosphere, it was showing this ratio increases to reach about 25%, with confidence of 80%.
Thank you very much, Mr. Sufyan.
Thank you.
There's also a question that is directed to Ms. Noor. So the question states that since your topic discusses the effect of cloud seeding over the UAE, are there any negative environmental impacts in the UAE that follow cloud seeding?
So seeding agents such as sodium chloride and potassium chloride are negligible when compared to abundant amounts in the atmosphere. So even silver iodide, which is considered toxic, a toxic material, is too fine and have no effect due to particleization of the chemical. So it basically turns into a non-toxic chemical once it reaches the surface, or it reaches the ground, sorry. Countries using those materials for over 50 years have made studies to actually examine or know the effects. The chemicals used it turns out that the chemicals used are friendly to the environment and to the ecosystem, meaning to the soil and underground water. I don't think there is any negative effect. It's been over 50 years and there is none.
Thank you for your answer, Ms. Noor. We have another question, if we can go back to Mr. Sufyan. How do you know which clouds are suitable for cloud seeding operations in the UAE?
Actually, the cloud seeding is implementing here for the searching for the cumuliform clouds. And usually, as well, the cloud seeding is the procedure to seed the base of the cloud. You need to have a good updraft. So we are searching for the proper portion of the cloud experiencing good updraft, and these only available with the cumuliform cloud or towering cumulus or so on. So only the cumuliform could be convective, could be towering cumulus, or so only these clouds are amenable or suitable for cloud seeding. So stratiform clouds has maybe different procedures such as the ionization process or so on. But you need the cloud that heat clouds that having good updraft to carry the materials from the base into the cloud to react there and start to make condensation, absorbing process, and coalescence, and so on.
Thank you, Mr. Sufyan. Just a reminder to any audience members who have any questions, please feel free to type your question in the comments section and also specify which speaker you would like to address the question. We do have another question currently for Dr. Dion. So this question is, how are the UAE REPS awardees making an impact on the global rain enhancement community?
I think this is actually part of the global community that's working here, because as you could have seen, the different projects are being conducted by scientists from around the world. I mentioned the statistics about how many countries are involved. So it has a significant impact. I think that you can actually say that this is a major part of the global effort in rainfall enhancement that's been spearheaded by UAE REP. So it's not something small that contributes to a bigger thing. It is really the big thing, I would call it.
Thank you, Dr. Dion. Okay, maybe we can give one more minute to see just if anyone types in any more questions in the comments sections. In the meantime, I would just like to say, of course, thank you very much for the amazing job everyone did. It was a very informative session, and it was so great to see all the different angles of, from the three of you on the topic.
Thank you very much. No questions.
We are not receiving any currently. I think those were all the questions the audience had, and that's a testament to how well you three gave your presentations. Everything was very clear. So I'd like to thank you, our speakers, for sharing your insights on the importance of rain enhancement as a key contributor to tackling global water scarcity. I am confident that the valuable knowledge gained from the presentations held during this virtual webinar will help all those interested in cloud seeding in expanding their understanding of the methods and techniques used in rain enhancement, both in the UAE and internationally. Please note that you can visit the Rain Enhancement Hub page on our website to watch this webinar, in addition to our future ones. We look forward to welcoming you to our next webinar and informing you about it through announcements on our social platforms and our website. Thank you very much for joining us today.